Imagine you have like a massive plumbing emergency. Water is just gushing everywhere.
Oh, a total nightmare.
Right, so you call a plumber, they rush over, but instead of bringing a wrench to fix this high-pressure burst pipe, they bring a bottle of drain cleaner, the stuff meant for a slow pooling sink.
Which is completely the wrong tool for the environment.
Exactly. And yet, inside our own bodies, millions of people are walking around doing the exact biological equivalent of pouring drain cleaner on a burst pipe simply because we fundamentally misunderstand what blood thinners actually do.
Yeah, that term gets thrown around way too much.
So today we're taking a deep dive into a stack of pharmacological notes and medical history focusing on antiplatelet drugs. We're talking about household names, like aspirin and clopidogrel.
The staples of almost every medicine cabinet on Earth.
Yep. And our mission today is to decode how these incredibly common drugs actually keep your blood cells from clumping, why they were misunderstood for over a half-century, and why the latest science has entirely flipped what we thought we knew about taking a daily aspirin.
It really is a profound shift in modern medicine. Because, like you mentioned, people use the term blood thinner as this giant catch-all umbrella.
Okay, let's unpack this. Why is that umbrella term so problematic?
Well, throwing that term around obscures a massive biological difference. To understand why swapping these drugs is like bringing drain cleaner to a burst pipe, we really have to look at how the human body actually forms a clot.
Right, the basic plumbing of the body.
Exactly.
Yeah.
Back in the 19th century, a physician named Rudolf Virchow outlined what we now call Virchow's triad. He realized that blood clots basically form for one of three reasons.
Okay, what are they?
There's damage to the vessel wall, a change in how fast the blood flows, or a change in the makeup of the blood itself.
So damage, flow, or the actual blood chemistry.
Right. And this triad helps us map out two completely different environments in your circulatory system, namely the arteries and the veins.
Okay, so the arteries are the high-pressure pipes taking blood away from the heart, and the veins are the slow-draining pipes bringing it back. How does clotting differ between the two?
So in your arteries, the blood is rushing. It is a high-shear, fast-flowing environment. When an arterial wall is damaged, say, by a ruptured cholesterol plaque, specialized cell fragments called platelets have to rush in.
Like tiny responders.
Yeah, and they aggressively stick together just to avoid being washed away by the current. They form what we call a white clot. Antiplatelet drugs, like aspirin, are designed to stop those specific cells from clumping in that fast-moving water.
And if that arterial clot happens in the heart, well, that's a heart attack. And if it happens in the brain, it's an ischemic stroke. So antiplatelets are the tools for the high-pressure pipes. What about the slow-draining veins?
That is the domain of the other major category, which are anticoagulants. Think of drugs like warfarin or heparin.
Okay.
In your veins, the blood is slow-moving, and sometimes it even pools, like, in the legs during a long flight. This environment allows a cascade of plasma proteins to slowly build this fibrin mesh.
So it's more of a gradual buildup.
Exactly.
Yeah.
It traps red blood cells and creates a red clot, which leads to conditions like deep vein thrombosis. Anticoagulants target that slow-building protein mesh. They do not target the fast-moving platelets.
Which means giving someone an anticoagulant for a fast-moving arterial clot or an antiplatelet for a slow-pooling deep vein thrombosis, that's a massive clinical error.
A huge mistake. They target entirely different biological systems.
Understanding this distinction isn't just like pharmacology trivia. I mean, for the tens of millions of people taking these medications every single day, it can literally be a matter of life and death.
Oh, absolutely.
But what blows my mind is that for the longest time, we were using these incredibly powerful tools without having any idea how they worked. How did we actually discover this antiplatelet effect?
Honestly, we stumbled into it. The raw materials for aspirin are ancient. Around 400 BCE, Hippocrates was documenting how chewing on willow bark and leaves reduced pain and fever.
Willow bark, right. But when did it become actual science?
The leap toward modern science happened in 1763 with an English clergyman named Edward Stone. He was fascinated by the fact that willow trees grew in damp, swampy areas.
Why does that matter?
Well, those happened to be the exact same environments where people contracted ague, which we now know was malaria.
Oh, wow. So he assumed the environment that caused disease might also, hold the cure.
He did, and he noticed that willow bark tasted incredibly bitter, very much like cinchona bark from South America, which was the known treatment for malaria at the time.
Makes sense.
So Stone started experimenting on himself. He was drying out willow bark, grinding it into a powder, and ingesting it to see if it would cure fevers. And it worked. He actually reported his findings to the Royal Society.
Self-experimentation by tasting swamp trees is a wild way to pioneer pharmacology, but it kicked off a chemical race, right? Chemists isolate the active compound salicin in the 1820s, and by the late 1800s, they're using a derivative called salicylic acid, which works for pain but is brutally harsh on the human stomach.
Yeah, that stomach toxicity was a major hurdle. So in 1897, a chemist named Felix Hoffmann at the German company Bayer synthesized a much more tolerable form, which was acetyl salicylic acid. Bayer marketed it in 1899 under the brand name aspirin.
And based on the sources, we should note a really important historical point here. Hoffmann's Jewish colleague, Arthur Eichengrun, played a vital role in directing the synthesis. It's a contribution that Bayer later downplayed and essentially erased under pressure from the Nazi regime.
Right, it's a very dark and complex origin for a drug that's sitting in everyone's pantry today.
It really is. But here is the craziest part of that timeline. When Bayer brings aspirin to market, they are selling it purely as a pain and fever remedy. For its first 50 years on the market, nobody had any clue that it touched blood platelets.
Not at all.
It's like a famous comedy actor suddenly winning an Oscar for a gritty drama decades into their career. We had the world's most popular painkiller, and we didn't know it stopped blood clots. Who finally made the connection?
That would be a small-town general practitioner in California named Lawrence Craven back in the late 1940s.
Not a big city researcher.
Nope, he wasn't working in a high-tech lab. He was just incredibly observant. At the time, there was this aspirin-laced chewing gum called Aspergum. Craven was prescribing it to patients who had just had their tonsils removed to help soothe the throat pain.
Okay, let me guess. Chewing aspirin right over an open surgical wound led to some obvious complications.
A massive amount of bleeding. His patients were bleeding unusually heavily from the tonsillectomy sites.
Yikes.
But Craven reasoned through this really elegantly. He thought, if this aspirin gum is causing excessive bleeding, it must be somehow inhibiting the blood's ability to clot. So he made a massive clinical leap and started recommending daily aspirin to his older, overweight male patients to prevent heart attacks.
And I'm assuming the medical establishment celebrated him as a visionary.
They completely ignored him. He published his observations in a small regional medical journal in the 1950s, but, he was just a GP. He didn't have large randomized clinical trials.
And he couldn't prove why it worked, right?
Exactly. He had no mechanism. He couldn't explain to the scientific community how aspirin stopped the clots. He was just a guy pointing at a phenomenon. Craven unfortunately died in 1957 without ever seeing his deductive reasoning vindicated.
So we have a drug we've used for a half century, a GP who correctly guesses its secondary superpower, and the scientific community refusing to believe it until someone maps the biology. When did we finally get that blueprint?
That happened in 1971. A British pharmacologist named John Vane cracked the code.
What did he find?
He discovered that aspirin works by inhibiting an enzyme called cyclooxygenase, or COX.
Yeah.
This enzyme is basically a biological factory that synthesizes certain prostaglandins. By inhibiting COX, aspirin shuts down the production of a very specific chemical called thromboxane A2.
And that was a huge deal.
So monumental that Vane shared the Nobel Prize in Medicine in 1982 for mapping this out.
Okay, we need to zoom in on this because knowing that Vane won a Nobel Prize for finding thromboxane A2 means we really need to understand what that chemical actually does inside a blood vessel. Walk us through the platelet playbook. When I cut my finger or when an artery ruptures, what is the sequence of events that builds a clot?
Okay, so there is a three-step sequence. Step 1 is adhesion. When a blood vessel wall is injured, the structural proteins underneath, like collagen, are suddenly exposed to the flowing blood.
Okay, so the foundation is exposed.
Right. Platelets recognize this damage and stick to the exposed collagen using a specific protein called von Willebrand factor, which acts like a biological glue.
So they adhere to the site of the damage. But a single layer of platelets isn't enough to stop a rushing arterial leak. How do they know to call for backup?
That is step 2, activation. Those stuck platelets start releasing chemical flare guns into the bloodstream. Two of the most important signals they release are ADP and, you guessed it, thromboxane A2.
Ah, there it is.
This creates a self-amplifying loop. They are chemically yelling for help, recruiting, and waking up all the nearby platelets that are floating past.
Which brings us to step 3.
Aggregation. The newly activated platelets physically change their shape. They swell up and deploy specific receptors on their surface. Think of these receptors, they're called GPIBI, as biochemical grappling hooks.
Biochemical grappling hooks. I love that.
Yeah, they use these hooks to grab onto a protein called fibrinogen, which acts like a bridge connecting one platelet to another. They rapidly cross-link, stacking on top of each other to form a solid physical plug. Adhesion, activation, aggregation.
And this sequence is exactly what John Vane realized aspirin was sabotaging. Aspirin targets that middle step activation. By destroying the COX enzyme, the platelet can't manufacture thromboxane A2. It cannot fire the flare gun.
You got it exactly.
But there is a detail here that completely bends my understanding of pharmacology. If you take a single low-dose aspirin, the drug itself is completely cleared from your bloodstream in like 1 to 2 hours, right?
Yeah, it has a very short half-life.
So if the drug is physically gone in 2 hours, why do surgeons require patients to stop taking aspirin a full 7 to 10 days before a major operation? If the chemical is no longer in the blood, shouldn't its effect be gone? It sounds like aspirin doesn't just block the door to the factory, it completely destroys the lock so no one can ever get back in.
That analogy is spot on. Aspirin doesn't just temporarily block the COX-1 enzyme, it permanently acetylates it. It irreversibly breaks the machinery.
But how does the effect last for a week?
Well, it comes down to what a platelet actually is. Platelets are not full cells. They are cell fragments that break off from larger cells in your bone marrow.
Meaning they don't have a nucleus, they don't have their own DNA.
Exactly, which means they physically cannot synthesize new proteins. They are essentially just bags of chemicals circulating in your blood. Once aspirin destroys that COX-1 enzyme inside a platelet, that platelet has no blueprint and no factory to build a replacement.
So it's just broken forever.
It is permanently disabled for the rest of its existence. And a platelet's natural lifespan in your circulatory system is about 7 to 10 days.
That is incredible. A single dose of aspirin permanently alters millions of platelets, and you literally just have to wait for your body to naturally recycle them and pump out a brand new batch from your bone marrow before your blood can clot normally again. It is a biological hit and run.
It really is.
No.
Now, contrast this messy, centuries-long botanical origin story of aspirin with the other major antiplatelet we see today, which is clopidogrel, widely known as Plavix.
Right, Platelets.
Clopidogrel is a marvel of modern linear corporate drug design. In the 1990s, the French pharma company Sanofi engineered it specifically to replace an older drug called taclopidine.
Why did they need to replace it?
Taclopidine worked, but it had a horrifying side effect of wiping out white blood cells and causing life-threatening clotting disorders.
So if aspirin stops the platelet from firing the thromboxane flare gun, how does this custom-engineered clopidogrel attack the clot?
It targets the exact same activation step, but it attacks the other chemical signal. Remember, ADP, the other flare gun.
Yeah.
Clopidogrel specifically binds to the P2Y12 receptor on the platelet surface.
Yeah.
That receptor is the docking site for ADP.
So aspirin stops the platelet from sending the signal, and clopidogrel destroys the receiver on the other end.
That's the core of it. By permanently blocking that receiver, the self-amplifying loop of platelet recruitment just sputters out. Even if the initial platelets adhere to the vessel wall, the surrounding platelets are deaf to their calls for backup.
Connecting this incredible biology to a real-world emergency, this mechanism is the exact reason why 911 dispatchers instruct you to chew an aspirin immediately if you suspect you are having a heart attack.
Yes.
In 1988, there was this massive study called the ISIS-2 trial. They gave aspirin to patients in the middle of heart attacks, and it reduced vascular mortality by about 25%, a quarter.
It's mass.
But the chewing is vital because digesting a pill takes time. Chewing it absorbs the drug instantly through the mucosal tissue in your mouth, sending it straight into the bloodstream to immediately hunt down and permanently disable those clumping platelets.
It remains one of the highest value, most immediate interventions in emergency medicine.
But manipulating the blood is a dangerous game. The body is always balancing on a knife's edge between bleeding out and clotting up. When drug designers try to engineer this process too aggressively, things can go catastrophically wrong. Let's look at the failure of a drug called Vioxx, or rofecoxib, which highlights exactly how fragile this balance is.
The Vioxx story is a tragic lesson in physiological balance. Standard painkillers, like aspirin and ibuprofen, block two types of COX enzymes, COX-1 and COX-2.
Okay.
We know COX-1 is the enzyme inside platelets that makes the pro-clotting thromboxane.
And blocking COX-1 is also what causes the infamous stomach irritation, ulcers, and gastrointestinal bleeding associated with these drugs, right?
Wow. Yes. Now, the other enzyme, COX-2, is found largely in the walls of your blood vessels. It produces something called prostacyclin, which is a powerful anti-clotting signal.
Oh, interesting.
It dilates vessels and keeps the blood flowing smoothly. Standard drugs block both the pro-clotting signal from the platelets and the anti-clotting signal from the vessel walls simultaneously, effectively lowering the volume on both sides.
I see where this is going. Drug designers looked at the stomach ulcers caused by blocking COX-1 and thought, let's make a drug that only blocks COX-2. We can cure the patient's pain, save their stomach, and just ignore the platelets entirely.
And by doing so, they tipped the biological seesaw completely over.
Wow.
By aggressively suppressing the protective, anti-clotting prostacyclin in the vessel walls, but leaving the pro-clotting thromboxane in the platelets completely untouched, Vioxx tilted the body's entire cardiovascular system toward thrombosis. It created a hyperclotting environment.
That's terrifying.
Estimates suggest this imbalance caused tens of thousands of excess heart attacks and strokes before the drug was finally pulled from the market in 2004.
So what does this all mean? We tried to engineer away a stomachache and accidentally caused a massive wave of heart attacks because we didn't respect the balance.
Exactly.
And sometimes the drug design is perfectly safe, but our own genetics refuse to cooperate. The mechanism behind clopidogrel has a hidden trapdoor called CYP2C19.
This is a fascinating quirk of pharmacology. Clopidogrel is what we call a prodrug. When you swallow a clopidogrel pill, the chemical you are ingesting is completely inert. It cannot block a single platelet in its original form.
Wait, really? So you are taking a chemical that isn't actually the medicine?
You are taking the raw material. It has to pass through your digestive system and into your liver, where an enzyme called CYP2C19 metabolizes it, physically altering the molecular structure to convert it into its active form.
Okay, so the liver does the work.
Right. Only after your liver manufactures the active drug can it enter the bloodstream and block the platelets.
But not everyone has a fully functioning factory, do they? Roughly a third of some populations with higher rates, noted in East Asian demographics, carry a genetic variant that makes them poor metabolizers.
Yes. Their liver simply doesn't produce enough of the necessary enzyme to activate the drug.
That's a huge problem.
A patient could diligently take their clopidogrel every single morning, entirely unaware that they are essentially swallowing a placebo. They get almost zero protective benefit against a heart attack or a stroke.
Oh, wow.
It is such a severe clinical risk that in 2010, the FDA mandated a boxed warning on the drug's label, alerting doctors that a patient's own DNA might render the medication useless.
That is terrifying to think about. You believe you are shielded, but genetically your armor is made of paper. Now, what happens when cardiologists decide to use both drugs at once? In 2001, the CURE trial tested dual antiplatelet therapy, or DTPT, essentially prescribing aspirin and clopidogrel together.
It is a very common strategy, particularly for patients who have suffered acute coronary syndrome or who have just had a metal stent deployed inside a blocked heart artery.
Because you really don't want that stent clotting up.
Exactly. By using DFPT, you are attacking the platelets from two distinct angles. Aspirin destroys the COX factory, and clopidogrel destroys the ADP receiver. The platelets are completely paralyzed. It is incredibly effective at keeping that metal stent open.
But going back to the seesaw, if you completely paralyze the platelets to protect the heart, you must be pushing the bleeding risk through the roof.
Every increment of anti-clotting power you add directly and unavoidably increases the risk of major hemorrhage. You are trying to keep a stent open in the heart without causing a life-threatening bleed in the brain or the gastrointestinal tract. It is the ultimate high-stakes balancing act in cardiology.
Which brings us to the most massive shift we're going to explore today. The razor-thin balance between preventing a clot and causing a bleed recently upended one of the most famous pieces of medical advice in history, the daily aspirin habit.
It is arguably one of the most profound public health reversals in modern memory, impacting millions of people globally.
For decades, healthy people over the age of 50 were told by their doctors, by public health campaigns, and by endless TV commercials to take a low-dose aspirin every single day.
The primary prevention strategy.
Right. Taking the drug before you ever had a heart attack, simply as a shield to keep your heart healthy. But around 2018, 3 massive clinical trials, ASPRI, ASCEND, and ARRIVE, dropped a bomb on this conventional wisdom. What did the data actually reveal?
These trials looked specifically at populations without established cardiovascular disease. They were healthy adults taking aspirin just in case.
Okay.
And the data showed that the slight reduction in heart attacks provided by the daily aspirin was entirely offset by a significant increase in major severe bleeding events.
Because, as we discussed, aspirin permanently disables the platelets. If a healthy person with clean arteries suffers a tiny microbleed in their brain or an ulcer in their stomach, they desperately need those platelets to patch the hole.
And they just don't have them. In fact, the SPR trial, which focused on healthy adults aged 70 and older, observed a highly concerning signal toward higher all-cause mortality in the group taking aspirin, driven largely by these severe bleeding complications.
Wow.
The drug designed to save them was actually pushing them closer to harm.
So within about 18 months of these trials being published, the American College of Cardiology and the American Heart Association completely flipped their guidelines. They essentially said, stop.
It was a massive turnaround.
Today, routine daily aspirin is almost exclusively reserved for secondary prevention, meaning you only take it if you have already had a heart attack, an ischemic stroke, or a stent placement. If you have known disease, your risk of a fatal clot is so astronomically high that it justifies the bleeding risk. But for healthy people just looking for a shield, the evidence completely collapsed.
The paradigm shifted entirely from everyone should take it just in case to only take it if your specific diagnosed risk warrants it.
There is also a major misconception about how we dose aspirin that feeds into this danger, the more is better fallacy. People assume that if an 81 milligram low-dose pill is good for the heart, a 325 milligram full-dose pill must offer like 4 times the protection.
Which is completely false.
Right. Taking a higher dose doesn't prevent more clots. It just guarantees more bleeding. Why doesn't the higher dose work better?
Because of the mechanism John Bain discovered. A low dose of aspirin is completely sufficient to maximally and irreversibly acetylate the COX-1 enzymes in all your circulating platelets.
They're already maxed out.
Exactly. Once those specific receptors are permanently broken, they are broken. Adding triple the amount of drug into the bloodstream doesn't inhibit any additional platelets. It simply exposes your stomach lining and other delicate tissues to severe chemical toxicity.
If you've ever had an older relative who is deeply confused about why their doctor suddenly told them to abandon a decades-long daily aspirin routine, this is exactly why. Science adapts when the data speaks.
It is the ultimate justification for why we must conduct rigorous, continuous clinical trials, even on medications we have confidently prescribed for over a century.
So we are looking at a complete paradigm shift. Let's recap this. We went from throwing an irreversible, platelet-paralyzing chemical at every single healthy adult, just in case, to realizing that manipulating the blood requires incredible precision.
Absolutely.
We learned that antiplatelets are for the fast-moving arterial white clots, while anticoagulants are for the slow-pooling venous red clots.
Completely different tools for completely different plumbing.
We discovered that a single aspirin permanently destroys a platelet's internal machinery for its entire 7 to 10-day lifespan, and that highly engineered drugs like clopidogrel rely entirely on a genetic lottery in your liver to even function.
It is a humbling reminder for anyone in the scientific community that human physiology will always be more complex than our assumptions. We trade clotting protection for bleeding risk every single time.
Which leaves me with a lingering thought for you to ponder. If a medication as ancient, as cheap, and as heavily studied as aspirin could have its primary public health advice completely flipped upside down in 2018 based on new clinical trials, what other universal medical truths sitting in our medicine cabinets right now are just waiting for the clinical trials of tomorrow to prove them wrong? Thank you for joining us on this deep dive. Keep asking questions, check your medicine cabinets, and above all, stay insanely curious.